Hey guys, in this video we're going to go over the 1.9 through 1.13 homework. Now as far as 1.9, we actually technically didn't cover it in the notes, but it shouldn't be anything that we can't do with what we already know. I think like the official name of 1.9, if you went to college, you're like My Classroom thing, and went to 1.9, it would be like connecting, had something to do with seeing a limit in multiple representations. So like seeing the equation, seeing the table, seeing the graph, and connecting them. So it shouldn't be anything too crazy. But if you do need any help with 1.9, and you can always just watch the videos that are in the classroom under 1.9. Okay. All right, so let g be a function that is increasing for x is less than 1. So I'm just trying to paint a picture in my head. So for x is less than 1, the function is increasing in some sort of way. So let g be a function that's increasing for x is less than 1 and increasing for x is greater than 1. So in some way it's increasing. It seems like always, except at x equals 1. So not really sure what it could be at that point, but if the limit as x approaches 1 of g of x is equal to 5, which of the following could represent the function g? So the limit as x approaches, I'm looking at the table right now, and I see that we're approaching 1 here, and then does it seem like we're approaching 5? It looks like we're defined to be 5 at x equals 1, but it doesn't seem like we're approaching 5, so I would say probably not this one right here. Doesn't look like it'd be 2. And looking at option 1, we have, well, let's evaluate this limit. It is a piecewise function. I'm going to take a look at this right here, and I'm going to factor that. So that becomes x plus 4, and then x minus 1 over x minus 1. So those cancel, and I'm left with x plus 4. And then, so this is a linear line, x plus 4, right? And then it says that at x equals 1, it's equal to 3, okay? I think it's just this graph down here. I think that these are the same graph, because 1, 2, 3, 4, and then at x equals 1, it's supposed to be equal to 3, but the limit as x approaches 1 is equal to 5. So it looks like 1 and 3 are the same thing, and it does look like that checks off what we need. So 1 and 3 only, not 2. Okay. The graph for question 2, the graph of the function f is shown above. Which of the following could be a table of values for f? Okay, so which of these tables could be for this one right here? So I'm going to note one thing before I go down to the next page, is that the limit as x approaches 1. So I see that the limit as x approaches negative 1 of f of x appears to be equal to 3, and then f of negative 1 is equal to 2. Okay, so I'm going to take these with me and make sure that this is what the table has. So the limit as, so at x equals negative 1, it's equal to 2. Negative 1, 2, negative 1, 2, negative 1. So it can't be C or D. So I'm going to cross those off right now, because we know that f of negative 1 is 2. F of negative 1 should be equal to 2. Okay, now we just need to make sure that the limit checks out. So the limit from the left side needs to be 3. It looks like that's what it's going to for both this side and the other side. Now on this side, approaches negative 1, it should be 3. That looks like it's 2. So it should be B right there. Okay. Example 3, let f be the function defined by f of x. So we have this function here. Which of the following statements is true? F has discontinuity due to a vertical asymptote. So I guess before I start, I'm going to see if I can simplify this, because that will help me decide what type of discontinuities there are. I can factor out an x. I'm just looking at the top and bottom. This has a common factor of x squared, but this one only has a common factor of x. So pretty much you'd have, let's say we have x, but then we'd have 3x plus 2. And then here we would have x minus 1. So the I'm going to do this with an x. So okay, so if I factor out an x, whoops, that should still have an x in it, 2x. This should be x squared. So I'm only factoring an x out, so those are going to cancel, which means if this is a common factor at x equals 0, you're going to have a removable discontinuity. So f is going to have a removable discontinuity at x equals 0. So I think that's B, C. F is not continuous at x equals 0, and I don't think that there's a vertical asymptote at x equals 0, because again that cancels. So removable discontinuity at x equals 0, but those will cancel, and I still have this x minus 1. That would make this right here a vertical asymptote. So not a jump discontinuity. So I think we gotta be at C. So we're going to have a removable discontinuity at x equals 0 and a discontinuity due to a vertical asymptote at x equals 1. Example 4, the graph of the function f is shown above. What are values of x for which f has a removable discontinuity? Okay, so removable discontinuity would be kind of like what you see both here and here, where the function could be defined somewhere else, but it could be redefined to be right here, thus making it continuous. So this function could be redefined at x equals -1 to be 3, and therefore it would be continuous. Now the function might not be defined at all, so this point wouldn't even have to be here, and it's still a removable discontinuity because we could define it there to be continuous. And so if I'm looking at this graph, I see two spots where that could be the case. I see x equals 1 and I see x equals 7. So you could define the function at 1, and therefore you could define it at 1 to be 1 and be continuous, and then you could redefine at x equals 7 from 1 to 0, and then it would be continuous. So 1 and 7. 5 does not work because if I redefine it from to be 3 to be 2, that would not make it continuous. We would still have this jump. The only way to make it continuous at x equals 5 is if this function right here was moved up to join it right there. All right. Question 5. Let me clear all this stuff out. So question 5 is a calculator problem. Let f be a function defined by what we have here. Which of the following statements about f at x equals -2 and x equals 3 is true? I don't, Now my question is if I can just factor this and not use a calculator. So I'm going to check really quickly. The numerator has a factor of x, and then that would have x minus 3, x plus 3. So that's the numerator. If the denominator is factorable, I'm going to do factor by grouping. That's going to be x squared and be x plus 1. And I can take out a 4 from this one, so minus 4. But then that would be 2x minus 3. So no, not factorable. Nope. Okay, so hence the calculator. All right, so let me jump to my calculator. Let's graph this right here. So we have x raised to the third. I'm going to put this in parentheses because this is a quotient. So x raised to the third minus 9x, close parenthesis, divided by, and then we're going to have x raised to the third plus x squared, and then minus 8x minus 12, close parenthesis. Okay, so we're going to use the graph and a table to kind of help us with this one. So if I graph this right here, okay, so I see that we have what appears to be an asymptote at x equals, I think, -2, which is what what we're looking at. So which of the following statements is true at f equals -2? So jump discontinuity. Nope, I don't think there's a jump discontinuity at -2. I think we have a vertical asymptote. And then what's happening at x equals 3? Is it continuous or is it removable? So how am I going to tell here? I'm going to go to my window and look at x equals 3. And it looks like there is an error at x equals 3. So while here, if I look at x equals 3, you might not be able to see it. You might might not be able to see it. But if I go to my graph or my table, we are undefined at x equals 3. It's an error there. So I'm going to say that there is a removable discontinuity there. So there you go. X equals 6. Or problem number 6. Sorry, just looking at this right here. Problem number 6. Let f be the piecewise function defined above. Which of the following statements is false? Alright, so we're checking pretty much, it looks like if I'm looking at the answers, we're checking for continuity at 1, 2, 3, and 4. So if I'm looking at 1, all of these 3 functions right here are dealing with 1. It looks like we're defined at x equals 1. Okay, so that means f of 5 is equal to 1. Now I need to make sure that the limit as x approaches 5 from the left of f of x is equal to the limit as x approaches 5 from x approaches 1. Sorry, that's x approaches 1. X approaches 1 from the left and from the right of f of x. I am not thinking straight right here. F of 1 is equal to 5. So the limits also have to be equal to 5 from the left and from the right for it to be continuous. So if I plug in 1 right here, I get 5, so that means the limit from the left is 5. And then if I plug in 1 right here, that's -4 plus 9, that's 5. So I think we're continuous at x equals 5. So this is true. But we're looking for what is false. Okay? Now let's check at x equals 2. So 2 is going to be in between here. And at x equals 2, we have this function. There is no discontinuity at x equals 2. This function has no discontinuity in it. So because that's linear and no domain restrictions. So we are continuous at x equals 2. At x equals 3, let's check that. So that's going to be these parts right here. So if I plug in 3 right here, that's going to be -12 plus 9. I believe that's going to be equal to -3. But at x equals 3, the function is 4. So already we have a problem. So the limit from the left is -3. I checked that here. And then the function is 4 at x equals 3. So looks like we have this right here. It's false. So no, it's not continuous at x equals 3. And then at x equals 4, just to check, so 4 would be in this interval right here, and this is continuous at x equals 4. No discontinuity there. Example 7, we have a student attempted to confirm the function f defined by this right here is continuous at x equals 4. In which step, if any, does an error first appear? Okay, so step 1, let's see what the student did in step 1. So in step 1, it looks like the student factored the function. I think that's a good call. And then in step 2, the limit as x approaches 4 of f of x is equal to the limit as x approaches 4. So he's evaluating the limit at x equals 4. He noticed that those could cancel, right? And so the limit as x approaches 4 would be 3/2. Okay, so I'm trying to think. So where's he going with this? So he knows that the limit of this function at x equals 4 is 3/2, and if he's trying to make sure it's continuous, then the next step should be to make sure that the function of f of x at x equals 4 is also 3/2. Okay, so the limit as x, he's just plugging in 4 in here. So he's plugging in 4 right here. Okay, and then he's getting 4 minus 1, which is 3. He's plugging 4 right there. 4 minus 2 is 2. So that seems like it's okay. The limit as x approaches 4 of f of x is equal to f of 4, so f is continuous. Well, okay. So he's identified. Yeah, that's the problem right there. Okay, so here's the thing about this student is that there is a hole. This right here is a hole, right? So the function is not defined at f of 4. Yeah. So this is what the function would have to be, but the function is not defined at 4 because of this hole. So if this were going to be true, this is what the function would have to look like. The function would have to be this right here. So x squared minus 5x plus 4 over x squared minus 6x plus 8. And this is for x does not equal 4, because this is not defined at 4, right? And then it would have to be, you'd have to state that this is also equal to 3/2 when x is equal to 4. This function has a hole right there. Now, what this student is doing wrong is that he is pretty much overlooking this function right here. So he's overlooking this function right here. He's plugging in 4 into this function, but this function and this function are only the same when x does not equal 4. So he's plugging it into this function, which is not the function that we want to plug it into, because we're essentially trying to figure out if this function is defined at 4, but that's not the case. So step 3 is his problem right there. You can't just plug it into the simplified version. That's kind of like a cheat. So that's his problem. He's plugging 4 into the simplified version. You can't do that. That's not the correct way to do that. So step 3 is wrong. Okay. All right. Example 8. We have another calculator problem. Let f be the function defined above. Which of the following conditions explains why f is not continuous at x equals 2? So why is this function not continuous at x equals 2? So I'm going to look at the denominator, because that's probably why it's not continuous at x equals 2. Excuse me. Can I factor the numerator too? Maybe not. I should stop trying to do this by hand when it says it's a calculator. So let's go ahead and throw this into a calculator. Let's graph this right here. So we have x to the third. I'm also going to put a parenthesis right here because we have a quotient. And then plus 2x. And then minus 12, close parenthesis, divided by, and then we're going to have 8 times by cosine of pi x over 2, I'll say. So pi x divided by 2. Okay. and then it's going to be plus 2x squared, and then close parenthesis. I think that's everything. Before I click graph, I'm going to click the mode button. So the mode button is to the right of the second button, and I'm going to make sure that we are in radians. If you're graphing any function and you have a trigonomic function, you better make sure that you are in radians. So here is this graph right here. Very funny graph. So let f be the function defined above. Which of the following conditions explains why f is not continuous at x equals 2? Excuse me. So neither the limit as x approaches 2 of f of x nor f of 2 exists. So if I plug into, so f of 2 is going to be equal to 8 plus, if I plug into right there, it's going to be plus 4 minus 12. So the numerator is 0. Let's check out the denominator. 8 times by cosine, and if I plug in 2 right there, that's going to be cosine of pi, plus, and then if I plug in 2 there, that's going to be 8. Now, cosine of pi is 180 degrees, and that puts it here. Cosine is -1 right there, so this would become -8 plus 8, which, okay, so yeah, it's definitely not, so I can't say for sure that the limit doesn't exist, but I do have a graph to check it, but f of 2 doesn't exist, so let's check and see if the limit exists at x equals 2. So if I'm looking at it at x equals 2, I think the limit does exist. It looks like, yeah, the limit is defined there, because the limit from the left equals the limit from the right. And then, let's see, b, the limit as x approaches 2 of f of x exists, but f of 2 does not exist. That seems to check out with what we just saw, but let's check c and d just to be sure. So both the limit as x approaches, we've already identified that it does not, that f of 2 does not exist, right? And so, yeah, so the problem with A is that one. Problem with C or D is that f of 2 exists. So B is the answer. Number 9. Which of the following functions are continuous on the interval from 0 to 5? Okay. Let's take, why are these so close together? You guys ever, like, think about that? Like, what? Like, come on. Sorry. All right, so for this function right here, I'm going to factor it. So we have x minus 3 over x minus 3 times by x plus 3. So this has a hole at x equals 3. So hole at x equals 3. It also seems like there's an asymptote, vertical asymptote at x equals -3. Now, -3 is not in this interval, but 3 is in that interval, so not 1. That's not continuous on that interval. Let's check 2. So x squared plus 9. Now, do not try to factor x squared plus 9 because this is not factorable. Okay, x squared minus 9 is factorable. This is not. Now, x squared plus 9, if you're going to check to see if this ever equals 0, you're going to have a hard time unless you use imaginary numbers, which we are not. Okay, so x squared plus 9 looks like this right here, where it sits at 9. This does not equal 0, and so it can't equal 0, so there are no discontinuities with this graph right here, so we're good, we're continuous there. And then for 3, the graph of the natural log of x minus 3, doubt that you guys might remember, but this right here is the natural log function shifted over to the right 3. So at 3 it looks like this right here. It's got a vertical asymptote here. So obviously this one right here will not be continuous on the interval from 0 to 5. And it's not even defined until you get beyond x equals 3. So 2 only. All right, for 10, which of the following functions is not continuous on the interval from negative infinity to positive infinity? Which of the following functions is not continuous? From negative infinity. Okay, so this function is continuous from negative infinity to positive infinity. It's a polynomial. Let's see right here. This cosine of pi x, this should be defined for all real numbers, so we should be good there. Now, d should also be, it's b right here. So the reason why d is continuous on the interval is because e to the x does not ever equal 0. The graph of e to the x, if you consider the graph, goes like this right here. It's got this asymptote at y equals 0. It never touches 0. It never goes beyond 0. So e to the x never equals 0. And so this x value could be anything, and this will never be 0. And so apparently this right here, this rational function, at some point, x to the third plus 3x squared minus 2x minus 5, at some point that's going to be equal 0, thus making that's going to have some discontinuities there. Question 11. So we have f of x is equal to ax squared plus x squared for x is less than 3, and then this for x is greater than or equal to 3. Let f be the function defined above, where a is a constant. For what values of a, if any, is f continuous at x equals 3? So remember that if it's going to be continuous, then f of 3 has to be equal to the left and the right side limits, okay? So what I'm going to do is I'm going to plug 3 in here, okay? We're going to plug 3 in. So then we would get a squared plus 9, and then next we would have, if I plug in 3 right there, that's going to be 6a. Okay, now, so this is what happens at x equals 3 for both of these functions. Now, they have to be equivalent to each other. These expressions at x equals 3 must be equivalent, so I'm going to set them equal to each other. A squared plus 9 has to be equal to 6a. And you can see that we have a quadratic expression, so I'm going to isolate the quadratic, so a squared minus 6a plus 9 is equal to 0. Okay? And then I'm going to factor this. What multiplies to be 9, and so minus 3 minus 3. So then this will be equal to 0 when a is equal to 3. And so there you go. At a equals 3, so at a equals 3 and x equals 3, these will be the same, which means the limit from the left and the limit from the right will be the same, and the function will be defined at that point to be the same thing. So that's that one. All right, looks like we have something similar in 12. The function f is defined above, where c is a constant. For what values of c is f continuous? Okay, so I'm looking at this expression right here, and we've dealt with these type of expressions before in the form of the limit as x approaches, let's say, how would I say it? So the limit as x approaches c, as x approaches 0. So the limit as x approaches 0 of sine of ax over ax is going to be equal to 1. Okay? Now, so if I take the expression that we have here, that's like saying the sine of 3x over 2 times by 3x, right? So I know that if I take the limit of this expression at x equals 0, so the limit as x approaches 0, now this is like saying 1/2 times by sine of 3x over 3x, and I know that the limit as x approaches 0 of this expression is 1, right? And so times by 1/2, this will be equal to 1/2. So I know that this expression right here is not defined at x equals 0 because of this right here, but the limit is equal to 1/2. Therefore, c, there's a hole there. So this function, we've graphed it before. I've shown you the graph before of a function like this. Kind of looks like a wave, but they get larger. And then as we approach 0, it's going to approach, in this case, it's going to approach 1/2. Okay, but there's a hole there. And then it does the same thing on this side. So that means we have to fill in that hole with this value right here, 1/2. So it's going to have to be B. All right, and then we have question number 13. It is a calculator question. This is looking like the same type of problem as these ones right here, except you're going to be using a calculator, and which is nice because you're basically just going to do this part right here. You're going to set these two equal to each other in a calculator and then find where they intersect. That's what you're doing right here. Okay, but first thing, you have to plug in these values right here because the limit from the left and the limit from the right at x equals -1 have to be the same. And so you have to plug you have to plug that value of x in first. So that's going to become 4 minus cosine of -1. And then this is going to be c plus 5 natural log of -1 plus c. So you're trying to see 4 minus cosine of -1. When does this equal c plus 5 natural log of -1 plus c? So that's what you're trying to figure out. Now you're just going to plug this expression into your graphing calculator. Instead of c, you can use x, okay? And then you're going to find out what this is going to be equal to. So going to the calculator, I might have to go back and forth between this window. So we got 4 minus cosine of -1. So 4 minus cosine of -1. That right there is a constant, just so you guys are aware. This is a constant value. There is no variable in here. It's all numbers. So this will be a straight line. Okay? And then we have x plus 5 natural log. So we'll do x plus 5 natural log of -1 plus x. So -1 plus x. And then we're trying to see if this, we'll just graph it right here. Okay, so now we just need to check and see where they intersect. And so to check their intersection on a calculator, you're going to press the second button, and then you're going to place the trace button. Trace button is the button second to the right, far right, next to graph, where you see that calc and trace. So you can click that right there. And then you have the option down here to find the intersection. So go down to it, you can click enter, and then it's going to say first curve. So if you move the cursor over to the intersection, so move this cursor over to where the intersection is closely occurring, doesn't have to be exact, click enter, and it should move the dot to the second curve, and you're going to do the same thing. So move the cursor over there, click enter, and then right above y equals, the y equals button, you can see that it says guess, question mark. You don't need to guess, just click enter again. And then you can see in those red values, that's what the intersection is occurring at. So when x is equal to 2.269, we'll say, so when c is equal to 2.269, these will be equivalent to each other. And that, in that case, it will be continuous. And so this value of c, which happens to be option A. And there you go. All right, that's all the multiple choice. And now we finally get to have a free response question. Let's do this. All right, so we have the graphs of f and g are shown above on the interval from 0 to 5. Also, it does say that no calculators for this one, so write a difference quotient that best approximates the instantaneous rate of change of g at x equals 2.5. All right, so we're going back to our first day. So for A, we're trying to write a difference quotient So whenever you see that a difference quotient, what does that mean? That means y2 minus y1 over x2 minus x1. Or in other words, you can say f of b minus f of a over b minus a. This is a difference quotient, okay? And remember, that's just average rate of change. The average rate of change formula is the difference quotient. And we're trying to find the average rate of change that best approximates the instantaneous rate of change at x equals 2.5 of at g. So let's go to g. And x equals 2.5 would be right here. So what's going to best approximate this? What difference quotient is going to best approximate it? This line right here is already linear. Okay, so if that's already linear, then we just have to take these 2 points right here. So we'll take f of 3, right? Or sorry, g of 3. We'll take g of 3 minus g of 2 over 3 minus 2. So g of 3 minus g of 2 over 3 minus 2. G of 3, what is g of 3? So g of 3 is 1, g of 2 is 4. So we'll just say 1 minus 4 over 3 minus 2. You honestly don't have to do anything else. Yes, you could evaluate it, sure, but on the AP exam, if a question like this ever showed up, you can leave it like this right here. You might even be able to leave it like this right here, and you'd get all points for that problem, okay? For B, let h be the function defined as the, so h of x is the composition of g and f. Find the limit as x approaches 3 of h of x, okay? So we have that h of x is equal to g of f, so g of f of x, and then we're trying to find the limit as x approaches 3 of h of x, which means we're trying to find the limit as x approaches 3 of g of f of x, which means we're doing limits of composition. So let's go through that. So first, the limit as x approaches 3 of f of x. So let's go. So we're evaluating the limit of the inside function. So the limit as x approaches 3 of f of x is equal to 2, and we're approaching it from above. So it's equal to 2 from above. Now we're going to evaluate the limit as x approaches 2 from the right of g of x. So the limit as x approaches 2 from the right side of g of x, and that's going to be equal to 4. So the limit as x approaches 3 of h of x is equal to 4. All right, C. Let k be the function defined by k of x is equal to 4 minus f of x times by g of x. Consider x equals 2 and x equals 4. Determine whether k is continuous at each of these values. Justify your answer using correct limit notation. Correct limit notation and checking for continuity. You have to, if you're going to get full points on a free response question that's asking this right here, you have to show that the limit as x approaches 2 from the left of, what do we say the function was? K of x. Of k of x is equal to the limit as x approaches 2 from the right of k of x, and this right here is equal to k of 2. You have to show that these three things are equivalent. There is really no, so it says using limit notation. So if you're not showing something like this, you are not getting full points. So let's find the limit as x approaches 2 from the left of k of x, and that's going to be equal to, I'm gonna write down what k of x is equal to. So k of x is equal to 4 minus f of x times by g of x. So it's going to be equal to 4 minus, okay, now we're going to evaluate the limit as x approaches 2 from the left of f of x. So the limit as x approaches 2 from the left or from the right is going to be 4. 4 minus 4. honestly, at this point, it's not even worth checking. The limit as x approaches 2 from the left of g of x, as x approaches 2 from the left of g of x is -1, but it doesn't matter because this is just going to be 0, okay? Now, you have to do the limit as x approaches 2 from the right of k of x. Okay, so we already did the limit as x approaches 2. We said that the limit as x approaches 2 from the right or from the left of f of x is going to be 4. So this is just going to be 4 minus 4 times by, I guess, if we check the limit as x approaches 2 from the right, that's going to be 4. It doesn't matter because this will be 0. So all that's left for us to check is that k of 2, what is k of 2 equal to? So if I plug that in, we get 4 minus f of 2 times by g of 2. So I'm just plugging 2 in. So this is 4 minus, what is f of 2? So f of 2 is 4. What is g of 2 before g of 2 is 4? Okay, so minus 4 times by 4, it's equal to 0. So we have shown that all of these are equal to each other. So k of x is continuous at x equals 2. And we have all our justification right here. This right here is all the work that you need. Okay? All right, and then let's check right here. Let's go to D. So values of f of x at select values of k, select values of x are given in the table below. Okay, what type of discontinuities does f have at x equals 1? So, I mean, I don't understand why we'd really need a table for it. So, values of f of x at select values of x are given in the table below. What type of discontinuity does f have at x equals 1? Based on the values in the table, what is a reasonable estimate for f of 1 for the limit as x approaches 1 of f of x? Give a reason for your answer. And so, so at x equals 1, so the limit as x approaches 1 of f of x, okay, limit as x approaches 1, okay, so that's why it's giving us the table to give us more precise values, because that's not happening at exactly like 1, 2, 3, or 4, or something like that. Okay, so what type of a discontinuity? That's removable, right? So for D, that's removable. That's more obvious from the graph, not the table. But I guess the table does support it. Okay, and then what is a reasonable estimate for this right here? So a reasonable estimate at what the limit would be to take these values, the closest values that we have to x equals 1, that's defined. So these are the closest values that we have that's defined around x equals 1. So if I just add these together and divide by 2, that would give me something directly in between these two values, which might give us a reasonable guess. So that's what I would show. So I would show 2.784 plus 2.787 divided by 2. And if you do that in a calculator, you can get 2.7855. So there you go. Say that the limit as x approaches, so what is a reasonable estimate for the limit as x approaches 1 of f of x? This might be a reasonable estimate right there. Okay? All right, and that's going to finish the video for this homework assignment.